Assalamu alaikum. Today we want to talk about chapter 14, part 1, chemical kinetics. The area of chemistry concerned with the speeds or rates of reaction is chemical kinetics. Our goal in this chapter is to understand how to determine reaction rates and to consider the factors that control these rates. Factors that affect reaction rates. Number 1. Physical state of the reactants. In order to react, molecules must meet each other. The more homogeneous the mixture of reactants, the faster the molecules can react. Example, a medicine in the form of powder dissolves in the stomach faster than in the form of a tablet. Second, reactant concentrations. As the concentration of reactants increases, so does the likelihood that reactant molecules will collide. So the rate is directly proportional to the concentration of reactant. If you look at this figure, steel wool burns slowly in air, 20% oxygen, but bursts into flame in pure oxygen. 3. Reaction temperature. Reaction rate increases as temperature is increased. At higher temperatures, reactant molecules have more kinetic energy. They move faster and collide more often and with greater energy, leading to increased reaction rates. 4. The presence of a catalyst. Now, catalysts are agents that increase reaction rates without themselves being used up. Catalysts affect the kinds of collagen and therefore alter the mechanism. Now, section 2, reaction rates. Now, the speed of a chemical reaction, its reaction rate, is the change in the concentration of reactants or products per unit of time. The units for reaction rates are molar per second. Now, if we look at this figure, shows us the progress of a hypothetical reaction A going to B. Notice here at the beginning we start with 1 mole of A, 0 mole of B at 0 time. Now, after 20 seconds, A is converted to B. So, concentration decreases of reactant and the product appears. 0.54 mole A and 0.46 mole of B. After 40 seconds, A decreases to 0.3 and B increases to 0.7. Now let's look at this sample exercise calculating an average rate of a reaction. Now from the data given in figure 14.3, we calculate the average rate at which A disappears over the time interval from 20 seconds to 40 seconds. So we are given the concentration of A at 20 seconds, 0.54 molar, and at 40 seconds, 0.3 molar, and asked to calculate the average rate of reaction over this time interval. Now, the average rate is given by the change in concentration, delta change in concentration divided by the corresponding change in time, delta T. Because A is a reactant, a minus sign is used in the calculation. So average rate minus. This minus means a decrease in concentration of A with respect to time. So 0.30 molar minus 0.54 molar, 40 minus 20 seconds, and the answer will be 1.2 times 10 to the minus 2 molar per second. You can solve the practice exercise in a similar way from the same figure. Now, change of rate with time. Now, let's see this reaction. Butyl chloride reacts with water to form butyl alcohol plus HCl. Now, the rate data for the below reaction. This is the rate data, time with concentration of butyl chloride. You see increasing time decreases the concentration. So in this reaction, the concentration of butyl chloride was measured at various times. Now, the average rate of the reaction over each interval is the change in concentration divided by the change in time. So the average rate, change in concentration of butyl chloride divided by change in times. So for each two values, you can calculate average rate, average rate, average rate, average rate. And as you can see, note that the average rate decreases as the reaction proceeds. And this is because as the reaction goes forward, there are fewer collisions between reactant molecules because concentration decreases. Now, instantaneous rate is the rate at a given instant during the reaction. For the same reaction, if we plot molar concentration of butyl chloride versus time, yields a curve as you see here. Okay. Now, the slope of a line tangent to the curve at any point is the instantaneous rate at that time. So if we want to measure the instantaneous rate at time equal 600, for example, we draw a tangent and we get the slope of that tangent to determine the instantaneous rate. Notice that all reactions slow down over time. Therefore, the best indicator of the rate of a reaction is the instantaneous rate near the beginning of a reaction. So what is the instantaneous rate at time equal 600? Here you see we draw a tangent as I told you, and then we get change in concentration of butyl chloride divided by change in time. You see here from 800 to 400, you see here, and then here 0.017 minus 0.042, and you will get this answer, 6.3 times 10 to the minus 5 molar per second. This is called the instantaneous rate. Similarly, the sample exercise 14.2, calculating an instantaneous rate of a reaction using the same figure. Calculate the instantaneous rate of disappearance of butyl chloride at time equals 0, the initial. So this is 0 time, you see. We draw a tangent. You see, this is the initial rate. And then we must determine the slope of the curve at t equals 0. And from that tangent, we can get the following values. So rate equal minus change in concentration of butyl chloride, the change of time. From the plot, we will get this value, 1.9 times 10 to the minus 4 molar per second. Also, you can solve the practice exercise from the same plot. Now, reaction rates and stoichiometry. Notice that in this reaction, the ratio of butyl chloride to butyl alcohol is 1:1. Thus, the rate of disappearance of tertiary of butyl chloride is the same as the rate of appearance of butyl alcohol. So rate minus change in concentration of the butyl chloride by delta T equal change in concentration of butyl alcohol by delta T. Now a question, what if the ratio is not 1:1 like in this example, 2HI to produce H2 gas plus I2 gas? So we can write here in such a case the rate equal minus 1 divided by the coefficient, then change in concentration of HI by change in time, and equal here the coefficient is 1:1, so change in concentration of I2 divided by change in time, change in time. To generalize then for the reaction, suppose we have this general reaction, we can write the rate equal minus 1 over A times change in concentration of A by change in time, equal minus 1 over small b, change in concentration of B divided by change in concentration, and this equal 1 over C, the same, and this is equal 1 over small d, etc. You see, the minus here indicates to the rate of disappearance of reactants, and here rate of appearance of products. Let's solve the following sample exercise relating rates at which products appear and reactants disappear. Now, how is the rate at which ozone disappears related to the rate at which oxygen appears in the reaction? 2O3 gas to give 3O2 gas. Now, B. If the rate at which O2 appears equal this value at a particular instant, at what rate is ozone disappearing at this time? So, again, using the coefficients as we said in the balance equation, we said the rate equal minus 1 over 2 change in concentration of O3 على change in time. And this will equal 1 over 3 change in concentration of O2 على change of time. Now, minus, we can move this 2 up to here. So minus change in concentration of O3 to determine this by delta T equal 2/3 change of concentration of O3 by delta T. So 2/3. Then 2/3 times this, if the rate at which O2 appears, this is the rate at which O2 appears, is this 2/3 times this, and this will equal the rate at which ozone disappears. And also here solving the equation from part A for the rate at which we have the same. Another method, but we get the same value here. Check, we can directly apply a stoichiometric factor to convert the O2 formation rate to the rate at which the O3 disappears like this. Now, concentration and rate law, section 3 in chapter 14. One way of studying the effect of concentration on reaction rate is to determine the way in which the initial rate of a reaction depends on the initial concentrations. For example, we might study the rate of the following reaction: NH4 plus aqueous plus NO2 minus aqueous to produce N2 gas plus 2H2O liquid. This table shows you the rate data for the reaction of ammonium and nitrite ions in water at 25. We have 6 experiments. This is the initial rate, different concentration, and also NO2 different concentration, and the observed initial rate for each one. Now, if we compare experiment 1 and 2, you see here, we fix the concentration of NO2 minus, and we see here, doubling the concentration of NH4, شو بعمل بالريت؟ doubles the rate. You see, doubles the rate. So the order of NH4 plus is 1. Also, if we compare experiment 5 and 6 here, fixing the concentration of NH4 plus, and here doubling the concentration of NO2 minus here, also doubles the rate. So also the order of the reaction order for NO2 minus is 1. So here we can say that rate is directly proportional to NH4 plus concentration, rate proportional to NO2 minus concentration. Therefore, rate is proportional to NH4 plus, this must be, times the NO2 minus, which when written as an equation becomes this. Then rate equal K times concentration of NH4 plus to the power 1 times NO2 minus concentration to the power 1. So we can say the reaction is first order with respect to NH4 plus and first order with respect to NO2, and it is second order overall. Now this equation is called the rate law, and K here is the rate constant, which is temperature dependent. Thank you. End of part 1.